Okay, recording
Good.
started.
Okay, so let's start. An introduction to MISRA C 2012. Here is a plan for the presentation. I will first say something about the behaviors of the C language that are not completely defined. I will explain why C is not fully defined and what are the consequences of this. And then I will introduce MISRA C. I will present the guidelines very briefly. I will show a selection of just 3 guidelines, and I will highlight that MISRA C has to do with prevention, not just with bug finding. And then I will draw some conclusion in preparation for the second talk I have, which is of a more practical nature. And the first one will actually last more than 30 minutes because for the second one, I came to the conclusion that it doesn't make sense to enter into much detail in the workshop. So I've learned something by following the previous presentation, I think. So first, a disclaimer. I am a member of the MISRA C working group, and I am also a member of WG14, which is the C language standardization working group. However, the views that I express in this presentation are mine and should not be taken to represent necessarily the views of the working groups. First disclaimer, there is another disclaimer. This webinar is only meant to introduce MISRA C 2012. It is not meant to suggest that Linux should comply with MISRA C 2012 or to suggest that Linux can possibly be made compliant with MISRA C 2012. So it's just an introduction to MISRA C 2012 so that when we talk about MISRA C, or maybe we will decide that we will never talk again about MISRA C, at least we know what we are talking about. So I will start with a question. So do you want to reason about code in assembly or in C? Well, if you want to reason about code in C, then we should make sure that the C code we are looking at means something. So the C language has several strong advantages, economic advantages. So first of all, C compilers exist for almost any processor, from tiny devices to supercomputer. C compiled code is very efficient without hidden costs, differently from C++, for example. And C allows writing compact code. There is a generous offer of built-in operators, and you can write quite complex things with limited verbosity. C is defined by an ISO standard, and possibly with extensions, it allows easy access to the hardware, which is, of course, crucial for embedded systems and operating systems. And C has a long history of usage, including in safety-critical systems. And moreover, C is widely supported by tools. So these are all good points about C. However, there are also significant disadvantages, and they come from the fact that WG14, the standardization working group, has always been faithful to the original spirit of the language that we can capture with this commandment. So it's a little bit of a joke. So trust the programmer, let the programmer do anything, and speed, and portability comes later. And as we know, these things are bad for safety and for security. So let us see where the problem comes from. Here I am quoting C99, but the situation is identical in C11, C18, in all the published version of the ISO standard. The problem comes from the notion of behavior. Behavior is something that is observable from the outside. It has an external appearance. And as a result of this definition, the compiler extensively adopts the as-if rule, meaning that the compiler can do any transformation that ensures the observable behavior is unchanged. Okay, this is not just true for C, it is true for many other languages. It is true for all languages that admit an optimized compilation implementation. Because in the as-if rule, we have many of the optimization opportunities that the compiler can exploit. So there are classes of behavior in C that are not completely defined. The most dangerous class is the class of undefined behavior, is when you use an erroneous program construct or erroneous data. And when you have undefined behavior, then the standard imposes no requirements. And no requirements means exactly no requirements. The program can do just anything. It may crash, may exhibit erratic behavior of any kind. It may even format the hard disk. This is a bit of a joke, but it's actually true. So if the hard disk is formatted because the program engaged the undefined behavior, it's your fault, basically. And in fact, what happens is that the compiler assumes that undefined behavior does not happen. If it does happen, it is the fault of the programmer. It's the programmer that has violated the contract, and there is no guarantee whatsoever. Let us see this by means of an example. One undefined behavior is when the program attempts to modify a string literal, meaning a string constant, a sequence of characters between double quotes. Here we have a small example. We have a string literal that contains 3 exclamation marks, and the programmer thought to neutralize 2 of them by writing to the string literal a null terminator in position 6. So this doesn't necessarily work because it's undefined behavior, and the program can do just anything. And one of the reasons, we'll see another reason, is that string literals may reside in read-only memory. And so trying to write something to them might result into an hardware exception. And at the language level, an hardware exception has any behavior you can imagine. So another class is unspecified behavior. This is slightly better. It's when there are 2 or more possibilities of doing something, and the standard gives no further requirement on which is chosen on any instance. So let us see an example. One of the unspecified behaviors is the order in which the sub-expressions of an expression are evaluated. So here we have an addition operator with 2 arguments, hello and word, and it is unspecified whether hello is called first or second. So if it is called first, then the output will be hello word, and this was probably the intention of the programmer. But it may well be the case that word is called first, and in this case, we will have the output word, exclamation mark, hello blank, which is probably not what is wanted. So it is important to realize that the only requirement of the standard is that one or the other thing happen. So there is not a requirement to document the choice. There is no requirement of consistency with respect to the choice. So the choice can change if I increase the optimization level, for example, or if I compile for debugging. Or I can complicate the example, and instead of returning immediately, I can compute this addition 5 times. And there is no guarantee whatsoever that the same choice is made in all the 5 instances. The compiler can do just anything. So if your program depends on unspecified behavior, it is ill-formed, meaning it has not a semantics, it is not a meaning. It is not possible to attach to it a meaning looking at the C code. You have to look at the assembly code if you want to know what happens. The third class is implementation defined behavior. So I will say little about this because everybody knows that there are implementations of C running on 16-bit machines where the size of int is 16 bits, and implementation for 32-bit machines where the ints are 32 bits. So the sizes of the basic data types are one of the aspects that are implementation defined by the language. And there are many more. There are more than 100 implementation defined behaviors in each version of the standard. And again, it is crucial for 2 things. So first, If you want to program in C, you have to know the implementation defined behaviors of your implementation. Otherwise, you don't know what you are doing. Okay. And secondly, if you don't take into account implementation defined behavior, portability is a problem. Now, why is C not fully defined? Why do we have so many behaviors that are not completely defined to the point of being completely undefined? We have seen three classes: undefined behavior, unspecified behavior, implementation defined behavior. And there is a fourth class, which is locale specific behavior, which is not so important for this discussion, even though it has similar issues as implementation defined behavior. So why is the language not fully defined? There are two reasons, again, economic reasons, because implementing compilers is easier, and moreover, because implementing efficient compilers, compilers that generate fast code, is easier. So let us see again the undefined behavior concerning trying to write to string literals. So in a compiler, due to the fact that this is undefined behavior, has the freedom of merging string literals. Suppose we have a program where there are two literals, one is tail and the other is head tail. It is perfectly legal for the compiler to just represent in memory head tail and return a pointer to the fifth character whenever a representation for tail is required. So if you change one of the string literals, you will change also the other one. You may change also the other one. So we have seen up to now two possibilities. You try to write to a string literal. Maybe you don't succeed because the string literal is in read-only memory and you get another exception. Or you succeed, you believe you have changed one string literal and in fact you have changed many string literals. So again, this is the compiler takes advantage of undefined behavior in order to reduce the memory footprint of the program in this case. Let us see another example which is instructive. Another undefined behavior is when an expression is shifted by a negative number, so when the shift count is negative, or by an amount that is greater than or equal to the width of the promoted expression. So let us start with the negative shift count. So it's undefined behavior. If C was not C, if it was another language, maybe this would be defined behaviors. What might it mean shifting a quantity minus 2 positions to the left? It might mean shifting 2 positions to the right. But if this was the definition of the language, then the compiler would have to insert for each shift operation a test of negativity of the shift count. In case it was found negative, it should have the shift count should be negated, and then the direction of the shift should be reversed. This is not the spirit of C. The spirit of C is if you want to play with negative shifts, you write the code to handle that. It is a little bit more interesting to understand why on earth shifting a 32-bit unsigned integer 32 positions to the left is undefined behavior. One might think, well, if I push 32 or more zeros to the right of this 32-bit quantity, then the result should be 0, right? No. No, because for very popular architectures like the Intel ones, the first thing that happens to the shift count is that it is masked. Only the 5 low-order bits are retained. And this is done in order to ensure a worst-case execution time, a low worst-case execution time to the shift instruction. So what happens is that in these machines, shifting by 32 means shifting by 32 positions masked, which is the same as shifting by 0 position, which is the same as doing nothing. So in the previous slide, we said we might have expected a 0 result, and in reality, what we obtain on this machine is something that may be something that the value is unchanged. So again, C leaves the behavior undefined for speed and ease of implementation. And this is a general principle of the C language. Whenever it is possible, an high-level construct of the language should be mapped to one machine instruction. And since there is a great variability between machine instructions, many aspects of the language are not completely defined. So let us start moving towards MISRA C. First, the history of MISRA C. So MISRA C, the work on MISRA C started in the 90s. At the beginning, there were Ford and Rover, and they were using their own in-house C coding standards. They merged forces under the umbrella of the MISRA project, and they produced MISRA C 1998, the first edition of MISRA C, which, as the picture shows, influenced basically all subsequent coding standards for C and C++. So we are now at MISRA C 2012. This does not mean that the last 8 years have passed in vain. MISRA C is continuously worked on. So amendment and addenda and technical corrigenda have been published, and so the development is incremental in preparation for the next roll-up release, which will be MISRA C 2020 something. So before showing the guidelines, I would like to stress the fact that the weakness of the C language comes from its strengths. So the good points and the bad points are tied in a very tight way. So for example, the fact that it is easy writing efficient compilers for almost any architectures, as we have seen, is one of the causes of non-definite behavior. We map high-level constructs to the machine instruction. The fact that it is possible to write efficient code with no hidden cost is because there is no runtime error checking whatsoever in the language. So if you want to check that your index does not exceed the array bounds, you write the code to check the index against the bounds. The fact that we have many compilers, today there are around 1,000 compilers in current use, and that the language is nonetheless defined by an ISO standard, then is another reason behind non-definite behavior, because the ISO standardization committees standardize existing practice. So whenever there are two compilers that do different things, do the same thing in different ways, often the only way forward is to have non-definite behavior. The fact that it is easy to access the hardware, it's the same reason why it's so easy to corrupt the program state. So it's easy, for example, to override the stack. And the fact that it is possible to write compat code has the same origin as the fact that it is so easy to misunderstand the language or to write completely obscure code. So several features of C are in sharp conflict with safety and security requirements. The solution that was identified by industry is called language subsetting, meaning that you don't program your code, your critical code in C, you code it in a subset of C, in which the possibility of committing potentially dangerous mistakes is highly reduced. So, language subsetting is mandated or recommended by all safety and security related industry standards, for example, ISO 26262 and all the others, basically. And today, the most authoritative language subset for the C programming language is called MISRA C, and this is why I'm presenting it today. So, MISRA C is a collection of guidelines. The latest revision with the latest amendment contains a total of 175 guidelines. And every guideline is classified either as a rule or a directive. The difference is this. If it is a rule, then it means that all the information concerning compliance is in the source code and in the implementation defined aspects of the toolchain. So remember, source code alone means nothing. You need to know the implementation defined behavior implemented by the toolchain you are using with the options that you are using for compilation and for linking and for everything. Okay? So it is a rule if, in principle, discounting the problem of undecidability of most interesting program properties. All the information is there so that the tool can, in principle, again, check compliance. Otherwise, a guideline is classified as a directive. It's a guideline where information about compliance is not fully contained in the source code and the implementation defined behaviors of the tool chain. You need to take into account requirements, specification, designs, and sometimes also the programmer intention. For directives, tools can provide significant help in checking compliance, provided you give the tool the missing information, the information that is not in the source code and in the tool chain. Another crucial aspect of the MISRA C guidelines is that they have a category. They are either mandatory or required or advisory. When they are mandatory, then a project can only be called MISRA compliant, MISRA C compliant, if the mandatory guidelines are all observed. If there is even a single violation, then the code will not be MISRA C compliant. So deviation is not permitted. Whereas for required guidelines, there is a choice. You can either comply or you can raise a deviation. Raising a deviation means writing a document explaining why you deviate and why it is still safe to deviate. So, and in case there is some risk, you have to assess the risk and describe which other activities are you doing in order to make sure that safety is preserved. Okay, and then there are a third category is the category of advisory guidelines, and these are recommendations. So they should be followed as much as possible, as much as practical. It's a choice. If you don't comply with an advisory guideline, you don't need to raise a formal deviation. You don't need to write a document. But at the end of the project, you have to list all non-compliances. So in the report that you submit to the assessors or to whomever, where you are making a claim of MISRA compliance, you have to list all the violations of the advisory guideline. I am simplifying a bit, but what I want is to convey the main ideas. So let's,
sorry to interrupt.
let me show you. Yes?
Sorry to interrupt. You have 6 more minutes in this for this particular talk, and then we are staying on the same bridge for the next one. So there is 1 or 2 questions. Do you want to do the questions, or how do you want to
yes. How can I see the questions?
There is one question it's in the chat session.
But I see only my slides.
Yeah, okay. You'll have to read it out.
Oops. Yes, I'll go ahead and read that out. Is MISRA C++ 2008 part of C 2012? Means C 2012 also includes C++ besides C?
No. MISRA C++ is a separate coding standard, which is today under review because it is being merged with AUTOSAR C++. And so no, it's a different thing. The same spirit. MISRA C++ is being revised so as to embrace the principles that were included in the transition from MISRA C 2004 and MISRA C 2012. So now MISRA C++ doesn't have this classification mandatory, required, advisory, and it will have in the next edition.
It just was influenced. So the 2012 version of C was just influenced by the 2008 C++ version because there was an arrow shown in your slide deck, which could indicate that C++ migrated into C, which doesn't make sense.
No. The meaning of this is that MISRA C 2004, ideas of MISRA C 2004 went into MISRA C++ 2008, and some further ideas were brought back to MISRA C 2012. Okay. Okay, so I want to show rule 1.1. This is required. It says the program shall contain no violations of the C standard syntax and constraints and shall not exceed the implementation translation limits. This is a very important rule. It says basically that the code must be written in C, in standardized C. And there are several reasons behind this guideline. First is that language features that are outside the supported version of C have not been considered when developing the MISRA guidelines. So if you use something that is beyond the standard, then you don't have the full protection you have if you embrace MISRA C. And secondly, a conforming implementation does not need to generate a diagnostic when a translation limit is exceeded. So now, for the kernel, this is not such, while the first point is important because the kernel is using basically all the extensions of GCC, and many of those are not standard. So, for example, when you have to qualify the compiler, you can buy a test suite, an industrial strength test suite for the compiler, but this will test the standard features, will not test the extensions. So someone else has to write the test for the extension. But anyway, GCC does not have very binding translation limits. So basically, as long as there is memory available in the system, GCC will compile everything. But you should know that in order for a compiler to be legitimately be called a C compiler, it has limits. It may, for example, not compile correctly code where there are switches with more than a certain number of cases, or the maximum depth of nesting of conditional compilation directive of the preprocessor. I think in C90 is 9. So if you have more than 9 levels, the compiler doesn't have to issue a diagnostic, and it may still generate an executable code, and you don't know what is in there. And moreover, there are many, and GCC is between those, is among those. There are many implementations that do not diagnose constant violations. So they accept code they shouldn't accept. It's code that violates the standard, and it is accepted even though it should have been rejected. And in fact, industry strength qualification suites for C compilers also have tests making sure that either illegal code is rejected or that you know that it is not rejected. And this is why it is important to use a separate tool to check MISRA compliance. Next rule is a rule about comments. So I have added it on purpose, so many people would think, what's the problem with comments? Well, comments are dangerous, and there are 2 or 3 guidelines in MISRA C dealing with comments. This one says you shouldn't use line splicing in conjunction with / comments. Line splicing is when you have a backslash at the end of a line, and this will cause 2 physical lines to be merged into a single logical source line. So, and here is an example where something bad may happen. So, critical function is presumably a function that was very important to call, and it is not called. Why? Because there is this comment before, which turns out to end up with a backslash. So the call to critical function is actually part of the comment. So it will not even be seen by the stages of the compiler past the very first one where comments are taken into account. Rule 13.2.
Sorry to interrupt again. This we have time is up for this talk.
No, actually, Shua. Shua, we said that Roberto could probably go up further on this one because he had more content here.
Yeah, because I will need much less time for the other
keep going. And then
and also nobody will go into the next session because the next session points to the same link. So I'm just joined again to the session by the other one.
Okay, we're all good then.
Yeah.
Okay, sorry. Yes. So, however, I didn't know what was probably expected. So yesterday, even though yesterday I managed to follow some of the presentation, so I got the impression that it was best to spend more time in this. And so Rule 13.2 says the value of an expression and its persistent side effects shall be the same under all permitted evaluation orders. This has to do mostly with unspecified behavior. So when there are two or more choices and there is no guarantee at the language level of which one the compiler will implement, but it has also to do with undefined behavior. For example, if you try to modify an object more than once between two sequence points, it's undefined behavior. For example, if you write something like I++ plus I++, this is undefined behavior. And let us see an example where unspecified behavior comes into play. So here we have a violation of the rule, and it's a violation because the order in which the arguments to a function call are evaluated is unspecified. And since the arguments are volatile objects, and reading a volatile is a side effect. Reading a volatile may trigger any side effect visible to the external world. So this is in violation because we don't know which side effect is triggered first, whether the one associated to reading TCNT1 or the one associated to reading TCNT2. So in order to make this code compliant, one possibility, the easiest possibility, is to introduce temporary variable and to sequentialize the accesses to the order that is wanted by the programmer. Okay, so this was just to give you an idea of what the guidelines look like. So we'll see another one in the second part, in the second talk. First, I want to emphasize this, that MISRA C cannot be separated from the process of documented software development it is part of. So MISRA C is not bug finding. It's not just, I will run a tool and I will find some bugs and I'm happy. And it's a completely different thing. Here we are talking about prevention. First of all, violation of a guideline is not necessarily a software error. For example, there is nothing intrinsically wrong in converting an integer constant to a pointer. And sometimes it's also necessary because you need it to access memory mapped registers or other features. However, since the conversions of integers to pointers are implementation defined, and also they have associated undefined behaviors, there is a rule in MISRA C that advises not to use them everywhere, apart from the very specific cases in which you need them and in which they are safe. So you see, it's not a violation of a guideline, it's not necessarily a bug. And the deviation process is an essential part of MISRA C. And in fact, apart from the mandatory guidelines, the point of a guideline is almost never, you should not do this. The point is, look, this is dangerous. You may only do that if it is needed, if it is safe, and if you can quickly convince a peer that it is both needed and safe. So if it takes half an hour to explain to someone else, or maybe to yourself 1 month from now, that this thing is safe, this is against the spirit of MISRA C. It should be obviously correct. It should take at most 30 seconds to understand that it is correct. And in fact, one useful way of thinking about MISRA C and the process is to consider it an effective way of conducting a guided peer review to rule out most C language traps and pitfalls. Okay, so in an ordinary code review, you will sit with your colleagues looking at the code. With MISRA C, you will have a tool that will help you doing the review, pinpointing places of the code that are not convincing, that are potentially problematic. Another aspect that places MISRA C in a completely different camp from bug finding has to do with reviews, in fact, code reviews, reviews of the code against design document, reviews of the design document against requirements. And in fact, many MISRA rules have to do with code readability and understandability. And another difference with respect to bug finding, I think that you can appreciate, I don't know if you follow the development of GCC and CLang, I do follow them both, and you can see that whenever there is a report of a warning that has a false positive, they will do just anything to silence the false positive, no matter how many false negatives are inserting. Okay, so the audience of bug finders is very intolerant to false positives, and they are tolerant to false negatives. But this is not a mindset that works in safety-related development. In safety-related development, false negatives are a disaster. Okay, so conclusion of this part, C is the most used language for the programming of embedded system, and the advantages of C come with corresponding disadvantages, and this is why we have language subsetting. MISRA C is, I believe, the most authoritative subset of C for the development of safety-related systems, especially embedded systems. MISRA C is part of a software development process that has very little to do with bug finding. So finding some bugs, yes, it's good, but it doesn't move things to the point where you want to bring them for safety-related development. And keys for smooth and successful adoption of MISRA C into an organization are good tools that are qualifiable as mandated by functional safety standards and proper training. I am mentioning this because training is essential in order to work properly with MISRA C. So if you have questions on this part, just tell me, and otherwise I will move to the other part.
Are there any good open source tools that are doing the MISRA scanning right now that are available to people?
No.
To work in their code base? No?
No,
okay.
Nowhere near.
Okay.
They're actually very, very bad. And the ones that are integrated, there are MISRA checkers that are integrated with compilers. These are also very bad. And the reason is that they recycle the static analysis algorithms that are used for optimized compilation. And these are governed by heuristics that have nothing to do with safety. So they give up very easily in order to ensure short compilation times.
Gotcha. Has there been any, has there been any discussion with the GCC community on this at all, or starting to look towards putting an option in or something like that to help make it better there?
Discussion with the GCC community about what?
About basically improving, the warnings and basically having the MISRA C being recognized a bit more officially.
Well, no, as I said, the audience is completely different. So they would just do anything to avoid the false positives, and they are not interested in
okay.
false negatives. So,
if I hear differently, really, I'll pull you into discussions. Okay.
I come from the open source world. I have been a developer of GCC. So, but it's really a different world. So it's a different thing. If you look on the internet, you will find that there have been at least a dozen aborted projects that started with the aim of producing an open source MISRA checker. They all failed horribly. So. No.
Okay. No, thank you. I just was curious.
Okay. So if there are no more questions, I think I have to stop sharing this and start sharing something else. So don't worry, I stop sharing this, and now I can share screen. And
Roberto,
I can...
just one question that maybe could be useful for ELISA community. We have already started to check something against CWD, then the security standards. Which is the benefit on adopting MISRA? Which is the different perspective let me say, between these two standards.
Oh, okay. So the benefit is that I probably forgot. Do you see my screen now?
Yes.
Okay. So the benefit is to gain the possibility of reasoning about code at the source level. So this was the sense of the first rhetorical question with which I started. So do you want to reason on code at the C source level or at the assembly code level? So if you do not rule out the undefined behavior, the unspecified behavior, if you don't take into account the implementation defined behavior, if you do not avoid the possible sources of confusion, then you will not be able to reason about the C code. So let's start with undefined behavior. If you have undefined behavior, the code means nothing. Okay, the code at the level of the source code. Okay, I will show examples in this part of the presentation because I have analyzed the Linux kernel, and I have just enabled one guideline, a mandatory guideline. It's a guideline saying that you shouldn't use the value of an automatic variable that is uninitialized. It's mandatory. So if there is one violation of this guideline, the code will never be MISRA compliant. So let me, okay, so I have run the analysis today on a configuration of Linux that is the configuration that was given to me by Lucas, if I remember correctly. And so this, I have analyzed a build that is simply the result of running make. So this compiled 4,000 translation units, and the linker was invoked 913 times. In total, 13,000 files were involved in this. And to give you an idea of what was the build that I've analyzed, so when the screen is shared, Control plus works, okay. So yes, the build that I analyzed was simply obtained by changing into the Linux directory and running a parallel make. And then here is what happened. So of course the compiler was called thousands of times, and let me show you. So for reproducibility, you can see from this offensively long report that the status of, for example, in sorry, there are so many files here. Okay. So this is the compilation of a translation unit that resulted into the production of this object file. The source files that took part in the compilation are this, and each one has its checksum so that the thing is completely reproducible, so that I can say exactly what I analyzed. Okay. So the command lines are also recorded, and because for working in safety critical things, you need the ability of providing evidence of what you did. Okay, so and there are 587 violations of this rule, which is rule 9.1, a rule that says that the value of an object with automatic storage duration shall not be read before it has been set. So why I am showing this? I'm showing this because this is a mandatory guideline that is directly related to an undefined behavior. Okay, so one violation is one undefined behavior. And so the idea is that if this information isn't accepted by the Linux community with the fixes that in most cases are trivial, then there is no chance any other patch will be accepted. So let us look at this. So the vast majority of the violations are due to this kind of thing. So auto-initialization. Okay, so a variable RCBA is declared here and it's initialized with itself. So it is this is straight undefined behavior. So this program means nothing. Okay, and the fact that I'm confident that GCC will do the right thing of this. But remember, do we want to reason at the source code level, or do we want to take into account the particular behavior of the compiler and the assembly code generated? So this is done a lot of times. You see, it's done on purpose. So there is a macro here, and this was done on purpose. It's a trick to suppress uninitialized variable warning without generating any code. This is what the programmer believes. The reality is this is undefined behavior. So maybe the warning was a false positive. Maybe the variable was not initialized. Here we have done two things. We have suppressed the warning, and maybe it was a true positive. And in addition, we have a 100% sure undefined behavior. Okay, so doing this is clearly something that that should not be done. And there are many of them. Okay, you see, it's in various places. It's usually done in macros. You see that here I can see the code before preprocessing, and when I move here, I see the code after preprocessing, and this allows me to understand why this happens. And here I can see the definition of the macro that does this. So once you have fixed this, and these are, I don't know, a few hundreds, as I said, actually fixing them, it's not clear what it means, because, okay, now it's undefined behavior. When we remove the self-initialization, maybe we will have other warnings saying that the variable is not initialized. Okay, and in this report there is a false positive. So this is something that we have already fixed in the current version of Eclair. And it's interesting. It was instructive to me to analyze the Linux kernel, because it violates so many of the MISRA guidelines that it is an interesting test. What do I mean? The false positive that is, I hope I will find it.
Roberto, quick question here. Which code base are you using for this analysis?
Sorry?
The code base used for this analysis, can you reference that? Code base.
Well, what is the code base? It's the one that I got from the thread, which originally was about the first experience with Coccinelle. I took exactly that code base. I asked on the mailing list for the kernel configuration. The kernel configuration was given to me, and I analyzed this. So, do you think it is very old? So you think that this self-initialization by design is no longer in current Linux?
So not sure. There have been bug fixes in this area. Because GCC, we have been enabling GCC options to find more and more of these, get more and more of these warnings. And people have been going around and fixing. I do not know if this particular, but 5.8 is it's not that old for the analysis you're doing anyway. We're at 5.9.
No, I think it's pretty new. So anyway, if you send me an email with instructions to reproduce any build with a configuration. I will run the analysis and let you know if the situation is the same.
Okay, great.
So to continue, what I was saying is that one of the things that MISRA forbids, I mean, it's not a mandatory rule. It is there is an advisory rule saying don't use GoTo. This is advisory, so you can use GoTo if you want. The advice is not to use them. And there is a required rules that says at least do not jump inside the block and do not jump backwards. Because if you jump backwards, then you are at the possibility of having loops, and the termination of these loops may be difficult to assess. And Linux is full of backward jumps. And as a result, so our algorithms were not so well tested in the presence of backward jumps, because as I said, backward jumps are not used in safety critical code. So when you really need a backward jump, the rule is required. You have to write a document, and in particular, you have to explain why you are sure that this will not result into an infinite loop or in a number of iterations that is too large. Okay. So now I don't know why the keyboard is not working. Okay, now I have this. So okay, here is another interesting thing. So this is not, as I said, the majority is self-initialization. So this is something that I don't know who introduced it into the kernel. It's certainly a bad idea. And here, but we also have different things. So here, the tool is saying that the offset field of this structure is uninitialized. So let us see if the tool is right or wrong. It may be a false positive. So BA is declared here. And some fields are initialized. BA.size is initialized here. The type field is initialized here, but I have checked it. The offset field is not initialized. I didn't find any initialization here of this field. So I think it is a true positive. But as I said, I have also spotted a few false positives due to how can I make this disappear? Okay, due to backward jumps and other features that make the code difficult to reason about. Okay, so let me. I don't want this to be too technical. So what? Here we have the count. We have 500 violations. So in Linux, there are millions of violations of the MISRA guidelines. Okay, and here I have shown only the definite violations. So when the tool says violation, it means violation unless there is a bug, and there is a bug because, as I said, I found and it was already fixed positive here that is false, and it should have been reported with the word caution, not violation. Okay, so when the tool is unsure about the fact that the positive is true, the instance is reported as a caution, and there are 30,000 cautions for just this rule, and so I am confident that many of those will, if really it was possible to analyze 30,000 of them, I'm confident that many of those will result to be non-problematic. But the point of the guideline is not this. okay, undefined behavior is important, but if you are working in safety critical code, 1 second after ensuring that every variable is initialized, you have to have an argument saying that the initializer is the correct one. So it's not enough for a variable to be initialized. It should be initialized with the proper value. So we see what I mean. So when the tool gives caution, it means that the code is difficult to reason about. Okay, it's in some cases it's really very complex. So there are backward jumps, jumping out from a switch, and it really takes time to understand this. This is not the spirit. The spirit is not only I want all my variables to be initialized, I want my variables to be initialized to the right value. Otherwise, it would be trivial to satisfy this guideline. I always initialize all variables at the point of declaration. Okay, and if the compiler is smart, if the compiler can prove that the initializer is useless because it will be overwritten, the unneeded initializers will be compiled out. However, there is a syntactic way of complying. So I'm just writing a random initializer. What I want to be sure is that I have the right initializer. Okay, so this is what I wanted to say, and I hope I have contributed to an understanding of MISRA C. Maybe you are disappointed by the second part of the talk. I think I will continue investigating the possibility for having some kind of compliance with respect to Linux. But if some of you is in contact with the maintainers, I suggest they start with this. So just drop me a mail. I will send you the report. You can produce a patch that removes this self-initialization. Of course, as I said, once you remove the self-initialization, maybe the compiler or even the tool will give warnings. In this case, you will have to question whether there really is a problem of initialization or not. Certainly, self-initialization was not the solution.
Alberto, can you share your report with Elisa development list?
Sure, sure.
Thank you.
So Roberto, a very interesting investigation.
Thank you.
I guess the problem is once you are doing machine, so programming close to a machine, you have to take care of two things. Number one, your compiler is broken. Number two, your hardware is broken.
Yeah.
So once you deal with those issues, there is no defined behavior as in any formal specification, right? Because you're already dealing with the problem that the hardware is broken. So there's already the hardware vendor already acknowledges that he's not following its specification. And the compiler already acknowledges that he's not following a specification. So the question is, what does that tell you when you have a coding guideline violation? I guess it tells you this code doesn't follow the specification, which is perfectly fine when you know that your compiler is violating the specification and your hardware is violating the specification. Right.
So let me try. I'm not sure I understand the the question. So for safety-related development, the functional safety standards put constraints on the way, depending on the criticality, on the safety integrity level, put constraints on how you develop and how you verify the hardware. Concerning the compiler, the specification is the ISO standard. And
well, but the hardware is broken. The hardware is broken by design. And even if you have compliance for the hardware, they never fix the hardware bugs. So they trick themselves out of that in a tricky way. That's the core problem.
So you say there is no hope, so we can
forget
about program correctness.
No, I mean, there's no hope in believing that you have formal specifications that are met by real life things, right? That's not what happens.
So unfortunately, the specifications we are talking about are not formal. They are informal because the ISO standard for the C language
they're probably
is informal.
I don't want to comment on Intel specifications, how they have been created, right? I mean, in some way, they probably are informal in that way, yeah. So yes, the question is, what's the point of showing some formal criteria when you know that the hardware is not?
No, if you adopt this point of view, we can all go home. The hardware is broken, so it doesn't even matter if the program what the program does.
Okay, so your recommendation is to not use broken hardware.
So it's not my recommendation. So it's the recommendation of functional safety standards to recognize that the hardware may have defects, trying to circumscribe
Lucas, what is the
and to work around the hardware issues.
Yeah, can I ask, Lucas, can you define what this broken hardware means?
Well, the files Roberto pointed out are called quirks.c and bugs.c. You know why they are called quirks.c and bugs.c?
No, I'm trying to learn. Sorry.
They are just full of code trying to work around hardware bugs and hardware quirks that simply don't work as they were intended to work. So they read back things and then they figure out, okay, wait, if I read back this strange register, then I know that by setting this strange value 3 times, the system works properly again. And if I don't do it, it will not work.
Well, these are called mitigations. You need mitigations also
but
when you use a compiler.
A mitigation doesn't need to follow a formal coding guideline, right? A mitigation is already at the point where you say, okay, I have to do something that's completely unreasonable just because that's what my hardware vendor told me to do when I encounter a certain situation. There's no, the argument is not it follows a formal specification. The argument is this is the quirk that we need to do to get it running again.
Okay, but behind this quirk, behind these mitigations, there will be a process that is regulated by functional safety standards that require testing, that requires...
agree. Yes, and that's of course in place. You just have to...
So can I read about this? Is this a standard practice, Roberto and Lucas?
So, well, yes, there are many compilers that have options that trigger workarounds for hardware bugs.
No, these quirks and these things seems like, is this a standard practice for Linux?
Let me answer from the Linux perspective. So yes, we do that because what happens is that there is a bug that surfaces on a old hardware or hardware bug that surfaces, and the recommendation from the maintainer and developers that are experts in for that piece of code or the driver would recommend a quirk. So this is clearly to work around hardware problems so that this hardware continues to function. Functionality wise also doesn't run into bugs. So it's so the process is documented in the sense that every single patch has to have a reason behind that. So it is going to be when a quirk patch comes in for a particular hardware, it is well documented why the quirk is necessary, and several reviewers do the review, and then the patch is accepted as a quirk. And then when the quirk is no longer necessary, they get removed. So that's kind of the background for that.
Okay. So then, Lucas and Roberto, maybe there should be a safe quirk and non-safe quirk kind of scenario, maybe. Like, I'm trying to manufacture over here. I understand, but I'm trying to figure out how. Like, this is a kind of a it is kind of a transitional mitigation, or this is from a factory point of view, like or manufacturing point of view. This is a needed step. So how do you do it safe? That's the question now, right?
Yeah, but your safety doesn't rely on a coding standard. Right? Your safety relies on a proper documentation of why your hardware is broken.
You're right. You're like the safety is an emergent, non-functional requirement. So what is that safety is? Is that all single point failures needs to be detected, and then
here it's much easier. Right? Here it's much easier. Here the answer is all the quirks and all the bugs in the hardware need to be reported to the OS provider, right?
Right, but I think what MISRA would do is basically trying to say
MISRA would just completely ignore the fact that you need to do undefined behavior to get the hardware working, because they simply assume that the hardware and the compiler work such that only defined behavior is necessary. Right? That's the basic assumption behind MISRA, which doesn't exist in that case.
So I think he has a tremendous misunderstanding ongoing, honestly, guys. Yes. So when it comes to hardware, there have to be fits met by the hardware, and if the hardware is broken, it should not be used in safety. However, that you have to deal with an issue in the hardware is no argument to not follow coding guidelines anymore. Yeah, it would be a little bit awkward to say, okay, now here I have an issue in the hardware, and now I'm allowed not to follow guidelines anymore.
Not to follow guidelines. What I'm saying is you need to judge, right? If this, I mean, the thing you want to achieve might only be possible by doing something that has no defined semantics in C.
Well, in this case, you program it in assembly.
Yeah, then maybe that's the solution. Yeah, that's true. Maybe that's the solution. Yeah, which then is safe, right? Because for assembler, you don't have coding guidelines.
Okay, so it's a bit late, and if you want to get in touch, please do it. I will be happy to interact with you by email and at the meetings of the various working groups in the future.
Thank you so much, Roberto, for your presentations and taking the time to do it. Thank you so much.
Okay, bye-bye.